So the first part of example 2 is basically what we did back in chapter 13. Here we know we have a normal distribution, and that's important. We know we have a normal distribution. You have to know that here. We know that we have a mean of 12 and a standard deviation of 0.2. We want the probability that a single can, so we're dealing with a single x here, is between 11.9 and 12.1. So let's start by drawing a picture just to give us a feel for what we want. We want this area between 11.9 and 12.1. So once you draw your picture, then we need to transform. Remember, these are x values. We need to transform those into z values. So the z for the mean is 0. The z for 12.1, since we're dealing with an x, it's x minus mu over sigma. So we can take 12.1 minus 12 over 0.2, and that will give us 0.5. So this is 0.5. You can do the same thing for 11.9, but you can also notice that this is the same distance from the mean, so it must be negative 0.5. If you use the formula, you'll get the same thing. It doesn't really matter. So finding the area between 11.9 and 12.1 is the same as finding the area between negative 0.5 and positive 0.5 for the standard normal distribution. So this is where you use your standard normal table, just like we did back in chapter 13. So if you look up 0.5, you'll get an area of 0.6915 or 69.15%. If you look up negative 0.5, you'll get an area of 0.3085 or 30.85%. So remember, when you're finding the area between 2 points, if you subtract those two, that'll give you the area that you are interested in. So in this case, that is 0.3830. So that is, don't forget, that is part 1. So part 2 is really what's new in this chapter. It's the same idea and almost the same process. So we draw our picture. Our picture is going to look exactly the same. In part 2, we want the probability that x bar is between 11.9 and 12.1 for n equals 16 cans. So here, the big difference isn't so much what the picture looks like, but the big difference is now these are x bar values. This is the distribution of x bar, no longer the distribution of x. Still the same process, though. We still want to change these into z's. The mean for the z's is always 0. So since these are x bars, we now use the formula from this chapter, which is x bar minus mu over sigma over square root of n. So this is the formula we use for the sampling distribution. So x bar in this case is 12.1 minus the mean. Remember, the mean of the x bars is equal to the mean of the population. Sigma in this case is 0.2. And that's over the square root of n, which we say we're dealing with n equals 16 cans. So if you work that out, in this case, it works out to be nice and neat. It is just 2. So this value is 2, and once again, it's the same distance, so this value must be negative 2. So now it's the same kind of process. We have a different z value, obviously, but we still use our table. We look up 2 in the table. If you look up 2, you'll get 0.9773. And you subtract what you get when you look up negative 2, which is 0.0227. If you subtract these, you'll get 0.9546. So when you take 16 cans, the probability that the mean of those 16 cans, randomly selected cans, is between 11.9 and 12.1 is 0.9546. So it's very similar to what we did in chapter 13. The big difference is you're no longer dealing with x, now you're dealing with x bar.